Okay, thank you.
Okay, thank you, Jaime. And first of all, I would like to thank the organizers of this geometry session for the invitation. So I have participated in the colloquium a few times as a student. So it's a great honor for me to participate this time with this opportunity to give a talk. Okay, so today I want to talk about the result about classifying constant mean curvature hypersurfaces in the real projective space, and discuss applications of that result to the isoperimetric problem. Okay, so the organization for this talk will be as follows. So in the first part, I will introduce the question of isoperimetry in real projective space, and also this definition of volume preserved instability, which is essential in our talk. And finally, I will state our main result and also some previous results on this classification problem. And in the second part, I will try to discuss the key ingredients and the key ideas that we use proving the main result. Okay. So the question we want to consider here is the question of classifying the compact regions in your Riemannian manifold, those that minimize the perimeter among regions of a given volume. Okay, so for us, the manifold will be mainly closed, but you can also assume it's non-compact, and for example, you can assume it's nice enough, like homogeneous, and that should be enough for our results. Okay. Right, so let me precise a little bit more this question of isoperimetry and introduce the main characters in our talk. We will say that a region that minimizes the surface area among all regions of a given volume, we'll call it an isoperimetric region, okay? And the boundary of that compact region, we'll call it an isoperimetric hypersurface, okay? So these are the main objects that we want to classify. Right, so another important object that we have in this discussion is the so-called isoperimetric profile, which is just the function that associates to each volume the area of the corresponding isoperimetric hypersurface, right? So in other words, what we want to do is just to describe this function and show it how it looks like, for example, okay? So let me start with the most important example, the example that motivates all of this discussion, which is the Euclidean space, right? So today we all know that the optimal solutions for these problems are geodesic balls. And out of this classification result, we have this beautiful isoperimetric inequality for compact sets in the Euclidean space, right? So we have many proofs of this result by now, but I guess the most famous one is the one that uses symmetrization techniques. And this technique is very appropriate in this setting because we have reflections with respect to any point and any direction, right? And so this important property is also available in the round sphere and in the hyperbolic space, right? And we have similar characterization there. Right, so if you want to consider this problem in general Riemannian manifold, so of course we don't have enough symmetries that you can use to characterize. So that's one of the reasons why this problem is very difficult in general, okay? So, so in that case, we divide the problem in two aspects. So there is the first part, which concerns the existence and also the regularity of these minimizers for this variational problem, right? And the other aspect, and this is the aspect we're going to focus on this talk, is the classification of this isoperimetric hypersurface in terms of the topology and geometry, okay? The reason we just need to focus on the second aspect is because we already have an answer for the first part of the problem. So this is a work of many people, and essentially under the assumptions we made on our manifold, the solutions exist and they are always moved except for a small singular set of Hausdorff dimension n-7. So if you are in lower dimension manifolds, for example, these objects are always smooth, okay? So after this result, some progress started to be made on other Riemannian spaces, and here I have a list of examples. And as you can see, most of the examples are of a product structure, so they still enjoy a lot of symmetries, right? And building on the previous regularity result, one thing you can try to do is to show that the isoperimetric regions is rotationally invariant, for example, right? And that reduces the analysis for the isoperimetric problem. So we also have some interesting result in flat spaces, three-dimensional flat spaces. The problem is not completely solved there, but great progress we have there. And if you are looking at general case, like we have a work of Johnson and Morgan, and also important work by Nardulli, which concerns small isoperimetric regions and Riemannian manifolds, right? And so they prove result that shows that these objects are nearly round in a way that you can precise, okay? And so if you look at the other side of this spectrum, large isoperimetric regions, we also have very interesting results that characterize large isoperimetric regions in the class of manifolds which are asymptotically flat at infinity, right? Asymptotically flat. And most of these results also prove uniqueness. So you have this beautiful description for these isoperimetric regions as something that foliates your Riemannian manifold, okay? Right, so this is a list of results that we have for the isoperimetric problem. So in this talk, I will focus on the variational perspective on these isoperimetric regions. So for that, it's important that we recall the main equations for critical points, okay? So here I'm going to introduce these two functional, the area functional, which measures just the area of a perturbation of your isoperimetric surface, right? You can imagine that you can deform your surface in the direction of some normal vector field on the surface. And then if you look at the volume between the surface sigma and the surface sigma t, so it's a sign volume, right? And if that sign volume is identically zero, that means that our perturbation is keeping the enclosed volume constant, okay? So that's the main type of variations that we're gonna consider here, okay? So the first equation that we have is, of course, that these isoperimetric hypersurface, they have constant mean curvature, right? And this comes from the first variation of area. There's a standard formula for that. And as you can see here, the mean curvature appears. And also this function f here, which is just the normal component of the variational vector field that you use to deform your surface, right? So it turns out that for our variation to be volume preserving, the integral of this function must be zero, okay? And the converse is also true. So for any function with average zero, we can always construct a perturbation that has the normal component, such function, okay? Right, so we are considering global minimizers. So in particular, they minimize area up to second order, right, for volume preserving variations. And we have also a formula for that second derivative of area, which is given here. And as you can see, this second derivative of area gives you a quadratic form on our surface sigma, and a symmetric quadratic form. And this quadratic form is always non-negative for functions that comes from volume preserving variation, right? And so the surface has this property. So in this discussion, the only thing I used was that I have a unit normal vector field along the surface, okay? And so we can include in this discussion immersed hypersurface, for example, and try to classify the hypersurface in which this quadratic form is always non-negative. And we use that as our definition of volume preserving stability, okay? So it will be volume preserving stable if the quadratic form above is always non-negative for functions that have average zero over the surface, okay? So if you can classify these objects, of course, that will imply some, will give some implications to the isoperimetric problem, right? It turns out that classifying these volume preserving stable is a very difficult problem, but if your manifold is nice enough and have some symmetries, you can still get some results, okay? So one important result in this direction was given by Barbosa, do Carmo, and Eschenberg in '88, where they actually introduced this definition in this general class of immersed constant mean curvature hypersurface and gave a very beautiful characterization for the geodesic spheres, okay? This is in any dimension. A few years later, Ritoré-Ros was able to classify also stable CMC surfaces in the real projective space of dimension 3, right? And so here in this case, we have examples of stable CMC surfaces, such as the geodesic spheres, but we also have some tubes about geodesic, and Ritoré-Ros proved that these are the only embedded ones, right? And so if you include immersed ones, then the only non-trivial, the only example is just the two-fold covering of RP2, which is, for us, is a trivial example. As far as our investigation is concerned, okay? So, right, and so our main result is a generalization of Ritoré-Ros to any dimensions, okay? So I will state our main theorem in a second. So, but before that, I'd like to at least state some key ingredients in the proof given by Ritoré-Ros and show you why it cannot be generalized to higher dimensions, right? So the proof essentially has two ingredients. So the first ingredient is this Hessian trick, which is a way to construct test functions for the stability inequality, right? And so essentially, this Hessian tree gives you a conformal map from your surface to the sphere with good upper bounds for the Dirichlet energy, right? And the crucial property here is that you can assume that this map has average zero over the surface. And the proof of that just use the group of conformal transformation in the sphere, right? So this is an ingredient that only available in 2 dimensions, right? And it's important to give you a topological control on these stable CMC surfaces, right? And so using that, they proved that the genus of this surface is at most 3 if you are in the real projective space, right? And the second ingredient is this Hopf quadratic differential, which is another way to construct some very interesting test functions. And they use this technique to characterize the surfaces with genus 0 and genus 1. So the genus 0 are totally umbilical, and the genus 1 are always flat, right? And so that is the part of ruling out these genus 2 and 3 cases, but then you just need to use some classical lower bounds for the Wilmore energy. So I'm not going to enter in the details of these proofs, but as you can see, these 2 ingredients are very 2-dimensional, okay? So some generalizations, still in 3 dimensions, we were able to show that this characterization still holds for other spherical space forms, more precisely those with large fundamental group. We show that if you have an isoperimetric surface, so here I'm talking about global minimizers, not, and you need to impose stronger assumption. We prove that they must be either spheres or tubes about geodesics. So these are the only possibilities, okay? So for the dimensions in between 2 and for the, so let me rephrase. So for the order of the fundamental group between 2 and these large fundamental groups, we don't have techniques at the moment to address this problem, okay? So another important previous result is a result of the Carmo-Ritoré-Ros, where they consider the case of RPN in many dimensions, and they gave a classification when the mean curvature is 0. Okay, so this is a very important work and was gave us a lot of motivation, and hopefully I'll be able to explain the similarities and also the key difference in our approach compared to the result. Okay, so now I can state our main contribution. So we looked at two-sided volume preserving inverse constant mean curvature hypersurface in the real projective space, and we proved that the possibilities are that sigma is a geodesic sphere, a tube, or these cliffal hypersurfaces, which you should understand as the generalization of tubes about geodesics that we saw earlier in the real projective space. So they are given by the product of two spheres, right? And they live in the round sphere, but they are invariant by the antipodal map. So if you quotient, you get a very nice embedded hypersurface in the real projective space. And also, we have the trivial example of a two-fold covering of RPN. So this is also a stable example, okay? So a few more words about these cliffal hypersurfaces. So as R goes from 0 to pi over 2, you get that these hypersurfaces are equidistant from one another, and they degenerate in some linear subsphere in the sphere, right? And so downstairs, they are equidistant from one another and degenerate in some linear projective subspaces. And so using that, these terms, we can give in very simple terms, the description for the isoperimetric regions in the real projective space. So they are just tubular neighborhoods of projective subspaces, right? RPK. So for example, when K is 0, there's just a point, and the tubular neighborhood are geodesic balls, right? And as the volume increases, then you get a tubular neighborhood of a geodesic, and so forth, okay? So that's the characterization for the isoperimetric problem. So of course, you need to address the possibility of singularities in higher dimensions, but we have a very standard argument for that, which comes from these good cutoff functions constructed by Morgan-Ritoré, which allow us to extend all of the variational argument that we use to handle these singular cases. So I will not discuss this technical part of the proof, okay? So what can you say about the isoperimetric profile, right? So here I have a picture for the isoperimetric profile of RP7, for example. And as you can see, all tubular neighborhoods appear as solution for the isoperimetric for some range of the volume. So if the volume is very small, then you get tubular neighborhood of RP0. Then as the volume increases, the tubular neighborhood of RP1 becomes better competitors, right? And then you keep going in that order. So in that sense, we have the successivity property for the isoperimetric profile, right? And in fact, we have a conjecture that this successivity property should be true in any projective space. For example, if you look at the complex projective space, you should also see similar picture, okay? Right. So let me see. Right. So now I would like to address some ideas that that we used in order to understand this problem in the real projective space, okay? And so, as I mentioned, the previous work of the Carmo-Ritoré-Ros for minimal surface was very inspirational, gave a lot of inspiration for us. And so it turns out that for the way the proof works, we need to divide the argument in two cases, right? The case where the volume preserved stable surface is minimal, and the case where the volume preserved stable is not minimal, right? The case where it is minimal, this is just the work of the Carmo-Ritoré-Ros, okay? So the key idea is to use, of course, the linear structure of the Euclidean space. So what we do is we look at the pre-image of our surface in the sphere, right? And so if you look at your surface there, then it's a codimension 2 surface in a submanifold in the Euclidean space. So in that case, we have two important vectors there, the position vector field and also the unit normal vector field, okay? And they satisfy good equations, which is given here, right? I'm calling them fundamental equations, okay? Okay, so the idea is to use these equations for the position vector field and the unit normal vector field in our stability inequality, right? Remember, the stability inequality comes from the fact that the quadratic form is always non-negative for functions with average 0 on the surface. Right. So how do Carmo-Ritoré-Ros prove the case, the classification when the surface is minimum, right? So they consider vector fields of the following form. So as you can see, it's a combination of the position vector field and unit normal vector field. You have this mixed product there, which is important just to make sure that this vector field is invariant by the antipodal map, right? Because in the end, we need to consider perturbations of our hypersurface inside the real projective space, right? So that's why we need the vector field to be invariant by the antipodal map. And we also have these two parameters there, these A and B, which are constant vector in the Euclidean space. And the role of this vector field, or of this vector B, is just to make sure that the integral of this vector field is 0, right? So that we can use the coordinate functions in the stability inequality, right? But of course, that requires some justification. Right, and so since our hypersurface is minimal, right? And so it's a long computation that you can do, and you will see that the quadratic form applied on the coordinate functions of this vector field gives you this expression, and as you can see, it does not depend on the parameter b, right? So being minimal allows you to look at this quadratic form only in terms of this variable a, okay? And so that's the key simplification that we have in the minimal case, okay? And so again, the question is, can you find B to make sure that the vector field is balanced, right? And so in their work, they prove this important lemma, which shows you that this linear map in B is an isomorphism, okay, in the Euclidean space. So since it is an isomorphism, so you can always choose B to make sure that the integral of this vector field psi is 0, so the vector field is balanced, right? And so once you get that the vector field is balanced and you look at the quadratic form, it should be non-negative, right? Because it's that comes from the assumption that the surface is volume preserved is stable, right? On the other hand, if you take the trace in A, you're going to get 0, right? Because the norm of the unit normal is 1. The norm of the position vector is also 1 because the hypersurface is in the sphere, so you get 0. So the conclusion is that this quadratic form must be identically 0, which forces this norm of the second fundamental form to be identically equal to n, right? And so now you get an equation for this minimal hypersurface, right? So it turns out that hypersurface in the sphere with which satisfies this equation has been classified way earlier in the literature. It's a classical result of Sharon, Carmo, and Kobayashi, which shows that minimal hypersurfaces in these properties are just Clifford hypersurfaces that I mentioned earlier, right? The product of spheres. So the remarkable thing here is that you have many topologies for these Clifford hypersurfaces, but they are all united in a single equation, which is this equation involving the norm of the second fundamental form. And this is a challenge to address the CMC case because we don't have similar characterization there, right? And the quadratic form is also algebraically very complicated. Okay, so now let's look at the CMC case, right? And so we still want to use the same similar vector fields, right? Because they enjoy success in the minimal case, so we still want to use them. And as you can see, there is a minor difference, which is this minus sign that appears before the first term. And this minus sign is not very important in the minimal case, but in the CMC case is very important, as I will explain in a minute, okay? So these are the vector fields. So if you look at the Jacobi operator on these vector fields, right? Remember that the Jacobi operator is just a self-adjoint linear operator associated to our quadratic form. And so I have an expression for the Jacobi operator on this vector field. And as you can see, when the mean curvature is not zero, then this constant vector B does not disappear, right? It stays there. So that brings a lot of difficulties in studying the quadratic form. So we also have this vector field capital X that appears there, but this vector field does not play a role in the quadratic form because it's always tangential to the surface. So when you take the product of this vector field with the vector field psi, you're going to get zero, right? And so here is the expression for this vector field X, right? And this vector field X didn't play any role in the minimal case. But in the CMC case, this vector field is very important because one of the observations that we noticed when we were working on this problem is that all Clifford hypersurfaces that I mentioned earlier are like they obey a quadratic equation on the second fundamental form, as shown here in this box. Okay. And so as you can see, the form of the vector field X is precisely the expression that appears downstairs, right? And so that explains the minus sign I mentioned earlier, okay? Right. So let me just say that umbilical spheres is also contained in this equation also, right? Okay. So it was clear to us from that observation that this parameter beta, or in other words, this vector B that we are considering here, they have some geometric meaning. So they should be related to the geometry of this Clifford hypersurface, right? And so our point of view was to try to understand the meaning of these parameters, right? And the key computation that we did was to show that these numbers has a variational interpretation, okay, as I will show you right now. Okay, so what is the main idea? The main idea is to look at the quadratic form evaluated on these vector fields psi, right? So here I need some flexibility in studying the quadratic form. So I need to introduce these other parameters, the parameter phi, which comes from an orthogonal map on the sphere, and also this parameter beta, right, which corresponds to any real number, right? And so if you look at this functional in this form, it will be a functional defined on a cylinder, right? Where the horizontal slice is just the product of the sphere and this orthogonal group, okay? Okay, so now we have a functional defined on this non-compact finite dimensional manifold, and we want to understand this function, right? So to do that, one natural thing you can do is just to look at the critical points, right? For example, for this functional. And the key computation that we did was to show that if you have a critical point for this functional, right, then that implies that the integral of the vector field psi defined earlier is balanced. So the integral is zero, so the vector field is balanced. So each coordinate functions of that vector field is a good test function for the stability inequality, right? And it's important to highlight here that the mean curvature must be non-zero, because if the mean curvature is zero, the functional does not, the functional is constant on the variables phi and beta, okay? Right, and so once we have this result, the natural thing to do is try to find critical points for this functional. And for that, we use the standard mountain pass variational principle, here in a finite dimensional manifold, right? And so as usual, we consider this max mean value associated to this functional, right? And so the picture is like this, right? So you look at the formation of your horizontal slices, which is represented here as this green hypersurface. And then you try to minimize the functional on this green hypersurface. And then you maximize among all possible deformations of that horizontal slice, right? That gives you a number, M1. Of course, you need to prove that is well-defined, but in the end will be well-defined, okay? And so the goal is to show that this number is a critical value for the function, right? And it turns out that the key important thing that you need to check in order to conclude that that number is a critical value is that the functional f satisfies this Palais-Meal condition, right? So the Palais-Meal condition is just a condition on a sequence of points on your manifold where the functional is bounded on the sequence, and the gradient of the functional evaluated on this sequence is getting close to zero in order, right? And so the Palais-Meal condition says that if you can extract a subsequence, then the number M1 there. So the Palais-Meal condition is just a condition that guarantees that you can extract a subsequence for that sequence, for that you can extract a convergent subsequence, right, for that sequence. And if that is true, then the standard mountain pass type argument will imply that this number M1 is a critical value, okay? And so how can you show that our functional satisfies this Palais-Meal condition, right? And so the point is, if you have a sequence where the function is bounded and the gradient is getting close to zero, but the sequence is drifting off to infinity, right? Then that's equivalent to look at, for example, at the last term of our vector field. If you normalize the vector field, the vector B there, so essentially, if that sequence is drifting off to infinity, is because the integral of the last term is trying to get close to zero. So you are trying to find a kernel for the linear map that appears in this lemma, right? And it turns out that this linear map is always an isomorphism, right? So this is a generalization of that lemma in the minimal case. And we have a similar isomorphism in the CMC case. And of course, here you just need to assume the surface is not totally umbilical, right? And so using that lemma, you can infer that the sequence cannot drift off to infinity, so it stays in a compact region on our cylinder, and so the Palais-Mills condition is satisfied. Okay, and once it's satisfied, then of course this number M1 will be a critical value, right? And another important property for this number is that it's always non-positive. Okay, that's very important for our argument. And the reason why it's non-positive is quite easy to understand, right? So essentially, if you look again at our cylinder, and if you pick the orthogonal map phi to be the identity, then if you look at your functional, when you fix this variable phi to be the identity, then the trace in terms of the vector field A is always 0, right? So that means that there is a direction A in which the functional is negative. And so if you look at this negative direction as beta goes from minus infinity to infinity, then you get a curve that will always hit the green hypersurface that appears here, right? And so in other words, there is always a point in our green hypersurface where the functional is non-positive. So that explains why this number M1 is always non-negative, non-positive, right? Okay, and that's good because remember that we showed that if you have a critical point, then the vector field is balanced, right? The vector field is balanced. And so by our assumption of volume preserving stability, that forces the quadratic form, or in other words, our functional f, to be non-negative when evaluated at that critical point, right? So M1 is greater or equal than 0. So combining these two information, we get that M1 must be 0, right? And now that we have a balanced vector field and the quadratic form is 0, then you just use the variational characterization for this type of functions, right? Type of functions. And so we get that each coordinate function of that vector field is a Jacobi function, okay? Meaning that the Jacobi operator evaluated on that function is a constant. So if you look at each coordinate, that gives you a vector C in the Euclidean space. The vector C here is just so it's in principle is non-zero because we are considering volume preserving variation, right? Just because of the volume constraints considerations that we are imposing in our problem, okay? But despite of that, you can look at the equation, right? And the equation is given here. And then you just need to study this equation, and it's not very difficult to understand that if you have something like that, that forces some restrictions on the norm of the second fundamental form. And in fact, we can prove that the norm of the second fundamental form is always constant, okay? That just comes from the equation above. And that's a very important simplification because once you get the norm of the second fundamental form is constant, then immediately we get a lot more critical points for that critical value, right? So for example, you can assume that phi 0 is the identity, and then for any A in the sphere, you have a critical point, right? You have a critical point. And then you can repeat the analysis of the Jacobi vector fields again. And so once we have this flexibility, now it's easy to show that C must be 0 in all of these cases, okay? And if C is 0, then it's because the normal component in the equation above is 0, and the tangential component is also 0, right? And the tangential component is, of course, that vector field x, which is given by this quadratic form on quadratic expression on the second fundamental form, A, right? And so, and this is true for any A, which forces the second fundamental form to obey that quadratic expression that I mentioned earlier, right? And that's the end of the proof, because once you get that, then the conclusion is that the principal, you only have at most two principal curvature, right? Because we have a quadratic equation in the principal curvature. So you only have two principal curvature at most, and they are also constant, because you just need to solve the equation. You're going to check that it's constant, okay? And so if you have only one principal curvature, that corresponds to geodesic spheres, right? And if you have two principal curvatures, that correspond to product of two spheres, right? And the dimension of these spheres will depend on the multiplicity of these principal curvatures, okay? And so once you get that, then it's a standard argument in differential geometry that you can characterize hypersurfaces with at most two principal curvatures, which are constant, and they are precisely the Clifford hypersurface that I mentioned earlier, okay? And so that gives you the complete classification of volume preserving stable, and in particular the solution for the isoperimetric problem. Okay, so so that's it. Thank you very much for your attention, and I'll be happy to answer any questions that you might have.